Okay, so now we're ready for chapter 7, which is our first look at continuous probability distributions. You recall that chapter 6 was our introduction to discrete probability distributions, where we specifically looked at the binomial and the Poisson probabilities. Now, in chapter 7, we'll be focusing all of our attention on by far the most important of all of the continuous probability distributions, and that would be the normal distribution. We'll see it all the time throughout the rest of this course and in stats decision making and any other statistics courses you may end up taking. It is used everywhere. Every discipline uses it. It's used on a regular basis, partially because it's very convenient, but because it does a good job describing the real world. And you'll see later on, as we get into more advanced topics, many statistical tests are based on the assumption that the data that we're using follows the normal distribution. So this may be the most important topic in the course, as far as using it again and again in the future. So anyway, we want to take a bit of a step back and explain how continuous distributions are different than discrete distributions, and then we'll introduce the normal distribution. So first things first, let's remember what it means to be continuous. It means that there's an infinite number of possibilities of our random experiment. So unlike, let's say, flipping a coin where there's a finite number of flips, or rolling a pair of dice, or whatever the case may be, with a continuous distribution, the number of possibilities is literally infinite. Like, here's a good example of this. Suppose we define the random variable x to be the time until the next phone call arrives. Now, of course, with time, there's a fractional component. It could be that it's 3.7 minutes until the next phone call, or 2.719 minutes, or 5.0188, or something like that. In other words, we're not restricted to integers like we are with rolls of the dice or flips of the coin. And all of a sudden, that means there's literally an infinite number of possible times until the next phone call. So that means that this random variable x that we've just introduced is actually what we will call a continuous random variable, and the probability distribution associated with it will be known as a continuous probability distribution. Now, formally, when we are dealing with a continuous distribution, the function that we'll be using to calculate probabilities is known as a probability density function. Now, what's unusual here is that, unlike with the discrete distributions from chapter 6, which could be illustrated with a histogram, like we see here, this would be an example of a discrete distribution. It doesn't have to be binomial or Poisson. What's important is that you have only 5 possible values of x, as you can see across here on the horizontal axis. The heights of these bars represent probabilities. And the most important thing is that all of these probabilities add up to 1, which they're required to do. And in addition, each one individually is somewhere between 0 and 1. In other words, we know that we're not allowed to have negative probabilities or probabilities that go above 1. So this is a perfectly valid discrete distribution. And in order to calculate, let's say, for example, the probability that x is between 2 and 3, what we're actually doing is calculating the 2 individual probabilities of 2 and 3 as shown by the heights of these bars, and we add them up, and you can see that we get a total area, or total probability, of 0.5. Now, why can't we do this with a continuous distribution? Because here's the holdup: you cannot use a histogram to illustrate a continuous probability distribution, because that would require an infinite number of bars. Okay, so in other words, here the number of bars is finite. We can't have an infinite number of bars. And what makes things even worse with the continuous case is that even if we did have an infinite number of bars, each one would have a width of 0, because you're representing a distribution with an infinite number of straight lines whose heights represent probabilities. In other words, it would look something like this. Okay, now it isn't really drawn properly. Those lines that you're seeing here, each one, since there would be an infinite number of them, each one would have a width of 0. And so while the heights do represent probabilities in a sense, the widths are zeros. So the way we approach continuous distributions has to be a little bit different than what we saw with discrete distributions. What we're going to do here is use geometry basically to calculate our probabilities. What we're going to do is, for example, if you notice how this curve up here in the upper right-hand corner, that represents some continuous distribution. And in order to calculate the probability that x falls between 2 and 3, rather than adding the heights of two discrete bars, we're calculating the actual area under the curve between 2 and 3. Now, the formula isn't here. I've made up this function, but there will be a formula involved that we can use to calculate the area under this curve between any two given points. And this is how we will calculate continuous probabilities. And by the way, I just want to point out here that the rules of probability haven't changed. The entire area under our curve has to add up to 1, because one of those outcomes has to be true with certainty. So what all of this implies, as you'll see in the next slide, is that we cannot define, or we will not be using probabilities for specific values of x. For example, with the phone call case, we'll not say, for example, what's the probability that it will be exactly 1 hour until the next phone call. We're going to define each individual probability as having an area of 0. Okay, so in other words, what we have to do instead is calculate ranges of probabilities. So instead of asking the probability that the next phone call arrives in, let's say, in a minute, what we could do instead is say something like this. What's the probability that the next phone call comes between 0.9 and 1.1 minutes? This is perfectly valid, okay? But to try to calculate the probability of the time being precisely 1, that by definition is equal to 0. So in other words, and that's because each of these lines has a 0 width. And so it has, in principle, a probability of 0 by itself. But when we combine it with some of the others, we can calculate probabilities for ranges of values. That we can do. All right, so in other words, no more probabilities that x equals a specific amount. It is simply a range that we're looking for. Okay, so that also means that when it comes time to the less than or equal to and greater than or equal to, we actually do not have to make a distinction here between the two cases. It seems a little strange. What we're seeing here is that, unlike the previous chapter, the probability that x is strictly less than some constant. Oh, hold on. Let's say, for example, let me just make up some numbers. It'll be a little less abstract here. The probability that x is less than or equal to 2 could be rewritten as the probability that x is strictly less than 2 plus the probability that x exactly equals 2. Now, in chapter 6, this would not have been a problem because we're dealing with discrete distributions. But here, this is going to equal 0. So therefore, these two are actually equal to each other. Okay. In other words, we don't need to make a distinction between strictly less than and less than or equal to. The same thing works with greater than or equal to. Okay, so for the same reasons, this last one is just 0 by definition. So therefore, these are equal to each other. Okay, so that's one of the consequences of us using a continuous distribution. All right, so just be aware of that. In chapter 6, it makes all the difference in the world if we're looking at less than or equal to or strictly less than, but here it does not. All right, so we're introducing the normal distribution. Now, just like with the Poisson and just like the binomial, it has its own formula that we'll use to calculate probabilities. Of course, as you can imagine, it's more complicated. Now, unlike chapter 6, where we solve those formulas ourselves directly, we're not going to do that here, okay, because that would require us to use calculus. So we have a couple of other options instead. One of them is to use the specialized calculator functions, and the second one is to use tables. Okay, now I've put on Blackboard the two standard normal tables, one for positive values and one for negative, and I'm going to show you both approaches. You may have seen the tables before, it's possible, and you can decide for yourself if you want to use tables or the calculator, but it's good to be able to do both, okay? So first things first, the formula for the normal distribution is very complicated. So what I'm going to do is instead of showing it to you directly, I'm going to show you a graph of this function. Okay. Now, unlike with the Poisson and binomial, where we illustrated those functions with histograms, here we're going to illustrate this with a curve. Okay. The curve actually, you have to visualize that the curve is essentially the tops of all the infinite bars connected to each other. And so it has a very special, unique shape. The curve that represents the normal distribution looks like this. And you can see it is often, because of the way it's drawn, it's often referred to as a bell-shaped curve. All right, this is what the normal distribution looks like. When you take the formula for the normal distribution and draw it as a graph, this is what it looks like. And some very important details to notice here. First of all, the curve never actually stops. Okay, if you notice down here, it converges to negative infinity. Up here, it goes to positive infinity. So in other words, it's actually covering the entire real number line. And the curve itself is what we're using to calculate probabilities. And like I said before, those probabilities are themselves simply areas under this curve. You can think of the horizontal axis, in fact, as an asymptote to this function, meaning that the curves are approaching it, but never quite reaching it. Now, there's two values that we need to know for the normal distribution. These two uniquely characterize it: the mean and the standard deviation. Now, if you notice, this is the same notation we used for populations in an earlier chapter. Why did they have to do that to us? Why didn't they pick out some new symbols? Well, they didn't. Okay, statisticians have been using this approach since the day this thing was invented. So we're going to follow along with that. So the mu, the first one is mu, if you recall. This represents the mean, in this case, of the normal distribution. Okay. In the past, we've used it for the mean of a population. Now we're using it to mean the center or mean of the normal distribution. And here's our old friend sigma, which is once again being used as a standard deviation, only this time it's the normal distribution instead of a population. Now, let me just show you some graphs. You might recall that we did something like this with the histograms in chapter 6. We saw how for the Poisson and the binomial, the shapes depend on, in the case of the Poisson distribution, the value lambda. For the binomial distribution, the shapes depend on the values of pi, the probability of success, and the number of trials. Well, here, the shapes depend on the mean and the standard deviation. So, and again, this is your standard normal curve. Oh, one more thing I think I forgot to mention. Among all the other amazing properties we have here, the entire area under this curve must add up to 1, of course. But what's even more interesting is that it is said to be symmetrical about the mean. In other words, the area to the left of the mean and to the right are actually mirror images of each other. They're identical to each other. This is something you don't always see with probability distributions. It's a very powerful feature. And so anyway, here's what we have. And this graph is here because I wanted you to see that the mean actually tells me the center of the distribution, in other words, where does it reach its maximum value, the standard deviation basically tells me how spread out the curve is. Okay, there's different ways it can be spread out, all of which, though, retain that standard bell-shaped curve look to them. So here's what I mean. Suppose I had two normal distributions. They have the same standard deviation, but different means. So if you notice, the shapes are identical to each other. And that's because the standard deviations are the same. What's different is their centers. The first one is centered at mu equals 0, and the second one is centered at mu equals 10. So the only thing that's different is their locations. It's like two mountains right next to each other, but the first mountain has a center of 0, the second one at 10, but because the standard deviations are the same, their shapes are exactly the same. Now, if we have instead two distributions with the same mean but two different standard deviations, their locations will be the same, but their shapes will be different, as you can see here. Oh, now this is an interesting case. The one in the center, this tall one, has a mean of 0 and a standard deviation of 0.5. The one directly below it, it's in the same location, it has the same center mean of 0, but it's far more spread out because that standard deviation is so much higher. So because of that, if you notice, there's less area near the center and a lot more area in the tails. Okay, so what that means is that with the second distribution, you're going to observe a lot more extremely large or extremely small values than you would with the first one. Okay, so there was the first curve, the tall one, has a lot more values very close to the center. The second one down here has a lot more values that are in the extreme tails. In other words, very, very large in the right tail and very, very small in the left tail. So here you can see it's the standard deviation that's determining the actual shapes. In other words, how spread out are they? But they're always bell-shaped curves. In other words, that part never changes. The only thing that changes with the different standard deviations is how spread out is the curve. Okay. And yes, just a quick reminder that we were looking at the binomial distribution, the two values that determine the shape of the histogram were the number of trials and pi. And when we were looking at the histograms for the Poisson distribution, what made the shapes different was the different values of lambda. So in other words, in all three cases, the distribution is actually an infinite class or family of distributions, each with its own unique values. All right, now I'm going to show you the formula, which we're never actually going to use this formula in the class, but I just wanted you to see what it looks like. This is the formula that we would use to calculate normal probabilities. And you can see it does contain the mean and the standard deviation. It has E, which we learned about, of course, in the Poisson distribution. Now, this pi, by the way, unlike when we were dealing with the binomial distribution, this is the pi you learned in high school. It's approximately 3.141, et cetera, et cetera, et cetera. And then sigma here is, of course, our standard deviation. So this is the formula that is used to calculate normal probabilities. And also, if you notice, instead of calling it P of X or something like that, when we have a continuous distribution, the normal convention is to refer to it as f of x, because it is, after all, just a function. It's a smooth, continuous function. So we'll call it f of x. Okay. All right. So, by the way, because there's an infinite number of possible normal distributions, just like with binomial, just like Poisson, it turns out, though, that there's one case which proves to be very, very important. Of all the different number of normal distributions that are possible, the one that we will use most frequently in a lot of applications is the so-called standard normal distribution, where the mean is 0 and the standard deviation is 1. Now, if you notice, I put a bunch of arrows there because I want you to remember this. And also I want to point out, when we get there, the tables are based on this distribution. That gives you a hint as to how important this is. The table wouldn't be based on this distribution unless it was important. Okay. Not that the others aren't important, but this is the most important. By the way, here's a point of notation too. You notice how up to this point we've used x's for all the different random variables. This is an exception. The convention is to use the capital letter Z to represent a standard normal random variable. So x could be anything, but Z is reserved. Now, it's not used for anything else. Whenever you see it, you can safely assume that we're referring to the standard normal distribution. All right. So the bell-shaped curve, actually, I did one of these in Excel so you can see it a little better. And again, the important details here, actually, this is the standard normal curve. You can tell because it's got a Z here and it's centered at 0. And then we have symmetry on either side. And if you notice, the tails go on forever. All right, now here's some interesting results. You don't have to memorize what I'm about to show you, but it's an important introduction to calculating normal probabilities. So what we're going to do is use the mu for mean, of course, and sigma for standard deviation. So the way we will interpret this is that, for example, mu plus sigma can be thought of as one standard deviation above the mean. If it happens to be the standard normal distribution, mu plus sigma would add up to 1. And you can see it's written right here. You see how I've got mu plus sigma, directly above it is 1. So what this means is that the mu plus sigma applies to all normal distributions. The 1 means that this is the standard normal. Now, mu minus sigma will therefore be 1 standard deviation below the mean. Or using the values 0 and 1, you could see that would add up to -1. So the probability that a standard normal random variable is within 1 standard deviation of the mean turns out to be approximately 68%, about 2/3. Okay. So the shading tells me, reminds me that this probability can be represented simply as the area under this curve between these 2 points. Now, how was that done? Well, that's going on behind the scenes. That takes a lot of messy calculus. Let's just take the word of the people who produce the tables and the formulas. Let's take their word for it that they've done this correctly when they set up the tables. So we're not going to do that ourselves. It's a bit of a mess, but you're applying calculus to that curve, and the result is the area under the curve between negative and +1, which turns out to be approximately 68%. Now, you can imagine there's a lot of potential uses for this kind of thing. Like, imagine that one day you're sort of wondering if next year it's going to be unusually rainy. And the thing is, if you assume that rainfall is normally distributed, you can find the mean and the standard deviation, and then you can come up with a formula and say, listen, what are the odds of the rainfall being within the standard deviation of the mean? And then this is all you would need to do. Now, what about 2 standard deviations above and below the mean? So this time, if you notice, the range is from mu plus 2 sigma down to mu minus 2 sigma. That it can be interpreted as 2 standard deviations above the mean down to 2 standard deviations below the mean. Or using the standard normal, that's the area between positive and -2. And this one, and we'll see how to prove this in a few minutes, proves to be about 95.44%. Now, by the way, the table is all listed as decimals, and so is the calculator. You don't have to interpret it as a percentage, but you can. In other words, 0.94544 is the same thing as 95.44%. So you can imagine how that would be helpful for let's say the grades on an exam. The vast majority of the people in the class should have a score within 2 standard deviations of the mean. Or think about it in terms of heights. The vast majority of the population's height should be somewhere within 2 standard deviations of the mean. If you're more than 2 standard deviations above the mean, you'll be so tall that people will probably notice it. You might be 6'7", let's say, but if you're also under 2 standard deviations below the mean, you might be 5 feet tall even or something like that. And then again, you might stand out because it's not that common to see people of those heights. Okay, so then for 3, we'll extend it out to 3. That's as far as we need to go. You can see overwhelmingly the majority of the area under this curve is within 3 standard deviations of the mean. Okay, now we can reproduce these anytime we want. We don't necessarily need these 3 for any particular problem that we're going to work on. What we're going to do now is jump ahead to the tables. Okay, now I've got them right here. They're posted on Blackboard. Here they are. So this is the -1. They're labeled normal table 1 and 2. The number one, this one is based on positive values. And if you look at this graph very carefully, these are all what we call cumulative probabilities, meaning less than or equal to. So here's how you can, the example I have here is 134. What if I need to know the probability Z is less than or equal to 1.34, which again could be interpreted as 1.34 standard deviations above the mean. So the way you look this up in the chart is you break up this number into 2 pieces. You can think of this as 1.30 plus 0.04. So I'm not going to obviously reproduce this whole table, but you're looking for the intersection of the 1.3. Just the 2 digits. I shouldn't have written it like this. Forget that 0 there. It should just be the 1.3 plus the 0.04. That's the way they've set it up. I'm not even sure if there's an eraser on this PDF. I'll find it later. But anyway, if you look carefully at the intersection between that row 1.3 and the column 0.04, where they intersect is 0.9099. So that shaded region is 0.9099 out of 1. Remember, the entire area under this curve is 1. So that's 90.99% of the total area under this curve. So you can imagine, again, in the case of exams, the chances are your score will be 1.34 standard deviations above the mean or less is about roughly 91%. Also, here's an interesting fun fact. This unshaded region, because the entire curve has to have a total area of 1, is just the rest. Okay. Did I do that right? No, sorry, that's so much. Okay, much better. And this area represents being greater than or equal to 1.34. So if the area to the left of 1.34 is 0.9099, all the rest of it must be whatever we get when we subtract it from 1, 0.9099, which is 0.0911. All right. So all of them are calculated the same way. These are all less than or equal to probabilities. We need to know in order to look them up, break it up into two pieces, this number and this number. The first two digits, the digit before and after the decimal, come from the first column, and the rest comes from the top row. The negative is exactly the same. This one is negative, they've chosen negative 1.34. So you're going to break it up into, now the way they've written it, it's a little strange. There's a negative down the first column, but not in the first row. I don't know why they're doing that, but this is the way it's done. You think they both be negatives, but oh well. Here's the negative 1.3, here's the 0.04. And as we predicted, it's 0901 because the two of them have to add up. Oh, I really goofed this thing up. It's 901, sorry. Yeah, that's what I get for trying to do it in my head. All right, so it's 901. The two of them have to add up to 1. That's better. Okay, much better. So that's how the tables work. And there's more examples here. For example, if you're looking for 1.0, this is just part of the table right there. You're going to look up the 1.0 in the first column. The 00 comes here in the top row, and that probability is 0.8413 or 84.13%. Okay. Now here's an interesting one. Suppose that the scores on an exam are normally distributed. The mean is 80 and the standard deviation is 8. Let's move this to the next page. So what that means then is that the probability, now let's let X be your score on the exam. The probability of that being less than or equal to 88. And so what you'll notice here is that 88 is one standard deviation above the mean. And so for that reason, this is the same thing as the probability of Z, which we did a minute ago. Oh, what do you know? How do you like that? So in other words, the two are equivalent to each other. And in a way, it's really no different than going back and forth between Celsius and Fahrenheit. The temperature, let's say the probability of it being at freezing tomorrow, 32 Fahrenheit, is the same as the probability of it being at 0 degrees Celsius because they're both freezing. So you're basically just converting, to use the tables, one set of units, in this case, grade scores, and you're just converting it into the standard normal form. Now, in general, though, there's a formula you can use to do this directly. And we'll get back to this later on anyway, so I'll show it to you now. To convert any normal random variable x to the equivalent standard normal random variable z, you can use this formula. So in other words, remember that in our example, the scores, the mean was 80, the standard deviation was 8. So the probability that x is less than or equal to 88, I apply this formula now, and I have z less than or equal to 88 minus 80 over 8, or less than or equal to 1. That I can just look up directly in the tables and I'm all set. If you notice, the table doesn't say anything about cases where the mean is 80 and the standard deviation is 8. It only talks about the standard normal random variable. Now, it's because of this transformation formula that we don't have to worry about it, because no matter what random variable we have, as long as it's normal, we can find the equivalent value from the standard normal table with this wonderful conversion formula. And by the way, when we do it this way, this Z is sometimes called a Z-score. Okay, so what I do is I took my X is less or equal to 88. And so now I suddenly have a Z-score of 1. So 88 for X is equivalent to 1 for Z. And in fact, we can see this by drawing two pictures, one on top of the other. What do I mean by that? On top, we'll have X. X is normal. Mean is 80. Standard deviation is 8. The center is 80. Now, what I'm going to do to make this as neat as possible, I'm going to copy this. Let's see. I didn't quite get it. There we go. This is Z, the standard normal. One on top is X, the scores on the exam. So an 88 would be, let's say, here. That corresponds to a Z-score of 1. Okay, so in other words, a probability of being less than or equal to 88, which would be all of this shaded region. Oops, sorry, wrong one. X less than or equal to 88 is equivalent to saying Z, the standard normal random variable, is less than or equal to 1. They mean the same thing, just like again with Celsius and Fahrenheit. The scales are different, that's all. So you can use the tables to calculate the probability for any normal random variable you choose once you've used that conversion formula. Okay. So now, just a hint, though, I'm going to show you a way of doing this on the calculator, which will make the tables, not that we don't need the tables, but not as important. So like, oh, here's an example. I wanted you to see how to do this negative, the negative side of the table. For negative 1.13, you're combining negative 1 with 0.03, and you end up with 1292. But once you see the technique on the calculator, you'll see that it's not absolutely necessary to have the tables. You will be able to decide which one you prefer. By the way, I just wanted to point out something. I hope it's still here. It's sort of a potentially helpful tool, but it can be a little quirky. Just by the purest of dumb luck, and I mean luck, I discovered that there is on the website of Texas Instruments a simulator of the TI-84 CE graphing calculator. You see, does it look familiar? Yes, there it is. So in other words, I can show you, not just by telling you what I'm doing on my calculator, I can show you on the screen what I'm doing. Yes. Oh my God. Now, here's the big question. How did I get to this point? If you want one of these, here's what you have to do. And by the way, I've noticed that sometimes you have to do it 2 or 3 times. It can get very quirky. If it flops on you, it doesn't work. The first time, just keep trying it again. What you're actually doing is typing. And I think this thing is case sensitive, but I'm not 100% positive. Oh, sorry, it's ti89.com. So that doesn't sound right, but that is correct. ti89.com. Now, online calculators, they probably have the other ones too. Don't put a dash in between TI and 84. Now that should bring you to a website where you are supposed to scroll down and click on the link www.testnav.com. Now, then you have to hit 2 start buttons, and the layout is very bizarre. And then you have to go to the top of the screen and click on the TI-84 icon. Now, in my opinion, it doesn't look very much like a calculator, but when you see it there, it's really the only icon on the top there. So in fact, I'll tell you what, maybe just to make sure that it's working correctly, what I'll do is I'll start this all over again so you can see how I did it. Okay. I mean, I'm reluctant to put this away because it's working, but let's see. But like I said, sometimes it doesn't really, it goes to a different website for some reason that doesn't work. And so, oops. I'll tell you what, I'll post this on Blackboard too, so we don't lose it. The beauty of this is that if you go to class and you forgot your calculator, but you have your laptop, you can still use this. But even from my perspective, it's easier to show you what I'm doing in the calculator when you can physically see what I'm doing, as opposed to me telling you what's going on in my hand. Okay. K89.com. Okay, so it's already there because I typed it in earlier. Okay, this time it worked. Sometimes it gets a little peculiar. Here's the link. Oh God, where is it? Oh my God. You see that? Oh, it's way down here. Okay, God. That made me nervous. Now, see what I mean? Start. This little tiny thing, although it's labeled at least, it's supposed to be a, yeah, just take their word for it. That's it. All right. So now we can use this thing. And it's been my experience so far. I mean, you always worry when you see these simulated calculators online if they really work properly or not. This one, so far as I can tell, is doing exactly what your calculator's doing, which makes me happy. So what we're going to see is how does one calculate normal probabilities on this calculator. But first, quick review of the properties of the standard normal. First of all, the probability of being in the interval from negative to positive 1, infinity rather, is 1. Because it's a probability distribution, the total area has to be 1. Something under here has to be true. Okay, if I remember, we talked about the example of the phone calls. The phone calls, something in here must be true, no matter what happens. The next phone call might be between 1 and 2 minutes, for example. But all of these collectively have to add up to 1. Because of the symmetry of the distribution, that implies that the probability of being below the mean, which is 0, has to be a half, and so does the probability of being above the mean. Because each one individually has to be the same, and then they have to add up to 1. That's the only way this can happen. Okay. Now, this is one thing we didn't talk about with the table. Actually, we did. We did have one example. I almost forgot. Yes, we did. If you have something like this, what if you have a greater than or equal to probability? The table doesn't show that, but what you can do is rearrange it algebraically. Now, why is this true? Because these two probabilities have to add up to 1, because one of them must be true with certainty. So there's, and we did see this example earlier. This is on the table. This one is not. So if I need this probability of being above 1, I can simply rewrite it as 1 minus the probability that's less than 1, and that is on the table. All right. So that's very important, especially with the tables, because the tables, like I said, only show less than or equal to probabilities. If you have greater than or equal to, this is what you have to do instead. And then if we find that the probability falls between two different constants, for example, something like this. Again, this is not on the tables, but you can work around that algebraically by rewriting it like this. Okay, because what you're actually doing is this. You're taking, imagine the area less than or equal to 1 would be, let's say, here. The area less than or equal to 2, I guess I'll make that red. I'll also make it, I'll put the slashes in the other direction. So the difference between the two is what you're really aiming for. And that would be this green section in here. What's left over when you subtract one from the other is what you're actually looking for. All right. So you can calculate any probability you need from those normal tables, as long as you are able to do the correct algebraic rearrangement as needed. Also, you can do any normal probability that's not standard normal by using that conversion formula, z equals x minus mu over sigma. So in other words, you can literally calculate any normal probability with those tables. It's just that you might have to do some converting. But what if you don't want to do that? What if you're like, I want to take advantage of the technology? I want to have some fun here. By the way, there's more examples here for you to practice with. I want to get to the table now. Let's start with this example. Now, this is a normal random variable. We have an experiment that consists of observing the returns to a stock. And of course, returns are percentages, and they can have a fractional component. So the number of returns that a stock can have is literally infinite. So we're going to say that X is the return to the stock. And we're assuming normality. That's without that, all of this goes out the window. X is normal. Yeah, that's got to be there. It's got, if it's not normal, then we're just wasting our time here. The mean is 5%. So I'm going to convert that to a decimal. The standard deviation is 0.02. So it's clearly normal, but not standard normal. So if I want to calculate probabilities here, I can certainly use my conversion formula. and take any values I need for X, convert them into Z-scores, and then I can calculate what I need from the tables. But I think it's high time that we open up the secrets of the calculator to do these probabilities. Okay, so let me just quickly remind ourselves that the mean is 5 and the standard deviation is 2. So this one is a cumulative probability less than or equal to 0.04. All right, here we go. Let's go to this calculator. And we're going to go to second vars, because you notice this in tiny little print, it says DASTR for distributions. The one we need is number 2. Oh, by the way, one thing you got to watch out for with the simulator, sometimes it accepts information by typing on your keyboard. Sometimes it doesn't. You just have to watch it. Like here, if you notice, I had to manually type this 2 here. Now, what's going on here? Oh, you know what I just realized? I can copy this. All right, it's trying to sell me something. Hold on. This is another good thing about. Oh boy. Yeah, I can just copy that right in here. Man, what a great discovery this was. So you have to give it 4 pieces of information. Now, what is going on here? We're assuming, first of all, that the curve goes up to positive infinity and down to negative infinity. So this is equivalent to saying X is between 4 and negative infinity. So remember, the mean was 5. And so 4% would be about here. And that's everything from that point down to negative infinity. So when you look at this, this is the lower limit of the probability that you're calculating. That would be this. This would be the upper limit. Now, the calculator doesn't have negative infinity as a keystroke. The way you work around that is this. Now, how do you implement this? You have to type negative second comma 99. If you type that correctly in the window, it'll replace it with negative 1E99, which means it's actually negative 1 times 10 to the 99th power. That's what we're going to use instead of in negative infinity, because the calculator doesn't have anything smaller than that. Upper will just be the 0.04. Now, remember, we said here for this case, the mean is 5. The standard deviation is 2. And when you're done, you hit that paste button, and I think you'll have to hit enter afterwards. So let's go back here and actually do it. Negative infinity is already there. I went with the arrow key down to upper, which is 0.04. The arrow key, I'm going to come down here and type, whoops, 0.05, 0.02. And then with my mouse, I'm going to hit the paste button. Now, you can do this on your actual calculator, and you should. You don't have one of these, or you don't have to have one of these. Now I'm going to hit enter again, and it's 0.3085. Okay. And that's my probability. of getting a return below at or below 4% next year, because the mean is 5% and the standard deviation is 2. Now, if you chose to use the table, you would have used this approach. So this would be the equivalent of saying, what is the probability that z is less than or equal to negative 0.5? And you would have found it right here. So either way, you'd still get the same answer. How about the next one? Greater than or equal to 8%. Okay, so you can see the approach using the normal table here. And remember, this is the mean, and this is the standard deviation. So if you calculate this using our formula, this is equivalent to asking what's the probability that z is greater than or equal to 1.5. Now, that is not less than or equal to, so we can't get this straight off the table, but we've already seen that this can be rearranged algebraically as simply 1 minus the probability that z is less than or equal to 1.5. And if you went to the table, you'd have this. Now, as far as the calculator is concerned, though, remember, we're looking at 8% and up. So what you have to do is second distribution. By the way, do not choose number 1, PDF. Just pretend it's not even there. It's always CDF. So now the lower limit is 8. The upper limit is infinity, which is implemented the same way as negative, but without the negative sign, of course. In other words, second comma 99. And there it is. Now, if you notice, it still has the 5 and the 2% here. It doesn't change those. So I'll scroll down, hit paste, and it's 0668. Oh, it's the same. How do you like that? It has to be the same. Now, there can occasionally be rounding differences between using the calculator and the tables. The tables are rounded. They can only show 2 places in the z-score, but they should be very, very similar to each other. So we'll wrap this up with the probability that x is between 4 and 7%. So I have to apply this formula twice, this conversion formula, if I want to use the tables. Okay, remember the mean was 5, the standard deviation is 2. So this is equivalent to asking what's the probability that z is somewhere between negative 0.5 and positive 1.0. And algebraically, remember how we work this out? Oh, yeah. It's in between. So therefore, we subtract the smaller probability from the larger one. Both of these run the tables. And you can see on the next slide, this one is 8413, and this one is 3085. The difference is 5328. Now, with the calculator, it'll be easy. You don't have to change too much. You just change the limits, 4 to 7. Let's go back there. Remember, don't forget, it's number 2. All I have to do is change this and let it rip. So in other words, paste. Oh, I have to actually arrow that one down. I'm still getting used to this thing. Your actual calculator, the one you hold in your hands, you'll get used to it pretty quickly. 5328. It's the same. How do you like that? So we're going to get a lot of practice with this, of course. We'll get some. We'll just actually do a bunch of normal probabilities just to get some more practice, and you can get out the calculator and learn how to use it by hand. It's virtually identical to what I was just showing you here. They did a good job with this thing. And then that way you can make sure you understand how to do it, because that it's going to come so helpful. I mean, incredibly helpful. So, I mean, that doesn't mean that I did post tables onto Blackboard if you want to use them, but it's up to you to decide which approach to use. All right. So anyway, now what's coming up next is an application of the normal distribution, which we'll save for next time. I think we covered all the most important details here. I think we're now pretty good at calculating normal probabilities, understanding their properties, understanding how they're different from discrete probability distributions. It's just all we really have to do now is get some more practice to really reinforce this. And you'll see that all the remaining chapters in the book and in the fall in stats decision making will most likely also involve the normal distribution. It's that widespread. So this is important to learn now. And so next time we'll look at this so-called normal approximation of the binomial, and maybe we'll do a bunch of practice problems, and then we'll move into 8, which is an application of the normal distribution. All right, so I'll see you all next time.